Welcome everyone. Thanks for coming. I'm going to get started. We have a lot to cover today, so hope that we don't get too rushed. I would ask you to hold most questions till the end. If there's anything that's really unclear or you think blatantly wrong, feel free to call that out. But I'll save side conversations until the end. Hi, I'm Andrew Twyman. This is my colleague Jacob Potter.
Hi.
We work at Dropbox on the cross-platform infrastructure team. What that means is we help build libraries and tools for building cross-platform code primarily aimed at mobile. And these are our three Dropbox mobile apps you can see across the bottom there. So we're supporting a multi-product code base as well as a multi-platform code base focused primarily on iOS and Android, though desktop and server platforms are on our roadmap as well. So here's a really brief overview of our architecture. We let our app developers build their UIs in the native language of whatever platform they use, or the natural language, I should say. We also want to take advantage of the platform's frameworks and services that are unique to that platform. So we do that in the language that it has to be done in. But we want to be able to write the core app logic, the business logic, the communication with the server, the data storage in C++ code so that we can share it across platforms. Now, between those two, obviously, has to be some kind of bridge to get you from one language to the other. And that is what we're here to talk about today. The specific languages we've been supporting for a couple of years now are Objective-C and Java, which are the preferred languages on iOS and Android. And the bridging technologies are the things that you have to use to get through there, and we have generation for those. As of today, this is not advancing, we also are adding Python to the mix, and I'm going to spend some time a little bit later on talking a lot about how we did that and what we learned from the process about kind of the general procedures of bridging languages. Before that, a little bit of context, and I want to poll the audience really quickly. How many of you have seen the talk that we gave at CppCon last year where we introduced Djinni? Okay, about a third. How many of you have actually tried out Djinni, the tool that we've open sourced? Mostly the same people, unsurprising. How many of you have done any kind of bridging of C++ to another language? Includes C, okay, almost everybody. So you've got some experience here. So I'm not going to repeat a lot of the higher level context that I gave last year. I encourage you, if you haven't, to go back and take a look at the talk. There's a link here that I'll give it again at the end of the talk, along with other links. But I'm going to give an introduction that's just kind of enough context to understand what we're going to talk about today, which is going to be focused on implementation techniques and technical details of how we did this. And all these details are not necessarily about Djinni only. They're about bridging languages in general. So I'm going to talk about what we did with Djinni, but you can generalize this to your own use as necessary. So what we are going to talk about, I'll do a quick review of the overview. I'm going to talk about how we added Python, the kind of problems we had to solve while bridging to it. And then we're going to have a deep dive into a couple different implementation techniques that are relevant across the multiple languages that we've done. So starting off with that brief introduction. What is Djinni? Well, Djinni is a code generation tool that we've open sourced that we use internally. It generates that language bridging layer that I showed in the architecture diagram earlier. If you're going to follow our architecture, let's say you're going to do Android and iOS, which is a pretty typical mix of platforms. You want your UI code to be able to call a common implementation. Your implementation might look something like this in C++, which is you've got a class, it's got a method you want to call, and you've got a structure that contains some data you want to pass to that method. Pretty basic stuff. So what do you have to do if you want to do this? Well, you need to implement the class that you're going to call. You need to make calls to it in Java and in Objective-C. And then you need to do one more thing, which is to describe your interface in a way that our tool can consume using the Djinni IDL. That's four things. Three of them you would have had to do no matter what you were doing. You know, you got to have a function to call. You got to have some calls to it. The one, which is the IDL, is what allows you to not have to do all the rest. So this is all the stuff that Djinni then does for you once you provide that IDL. It provides abstract classes that represent your model class in all of the various languages where it's needed. It provides concrete classes for your data structure that you're going to pass. And then it provides all the bridging that allows you to marshal these things back and forth between languages. When it's doing that, these are the basic principles that we're following. One very important one is that we want developers to be able to interact with natural-looking code in whatever language they're using. If you're making a call from Java that happens to be implemented in C++, that doesn't mean you should follow some arcane syntax or know about JNI or anything like that. We want you to just make a method call as if it was a Java object and have things work. The way we pass control between languages is we make method calls. We're not doing serialized RPC. We're not going out of process. We're not doing protobufs or something like that. We want things to just be calls with arguments and return values. The interfaces that are callable can be referenced from any language, meaning you can implement them in one place, call them in another place. Doesn't matter which one, as long as you put a couple decorators in your IDL saying which ones you would like to work, because they can generate different code. And then when you pass data between languages, it actually gets copied. Only once, but because it has to be different types in different languages, we couldn't really get around at least one copy being made. Djinni supports these basic custom types that you define in your IDL. Interfaces are like an abstract base class in C++. You can implement it in any language, call it from any other language. We have records. Think of those as structs. They're immutable, or at least immutable through the bridge. They are marshaled by copy, as I mentioned, and they contain other data, which might be records, might be containers, might be primitive values, but not interfaces. And also, they contain things by value, therefore there's no recursion. This isn't a tree that you're building out of your record, it's just a record. And lastly, we have enums. They're like a scoped enum in C++. Those are very basic. They're just there so that you can keep your values in sync between languages. You don't have to worry about somebody changing an int value or adding one. Of course, we've got all the other stuff you need to go back and forth. I'm not going to go into detail on most of this. One interesting one to mention, though, is optionals. How many of you have used optional, whether it's experimental optional, boost optional, something like that? Okay, a couple people. This is basically just a nullable value type. So you can return something or pass something by value, but you can either give it an object or not give it an object without having to resort to the heap and pointers. We use that a lot in Djinni interfaces. Here's an example of what Djinni IDL would look like. So you have an enum with a few values. You've got a record, can contain that enum, contain a string. This record is asking Djinni to create equality comparison and ordering comparison operators for it automatically. Then you can have an interface. This interface is declared so that it can be implemented in either Java or Objective-C, not in C++, but you could add a +C there if you want to do the other direction as well. And then this interface has some methods. It has a static method, which is useful as a factory, so you can create one in the first place, and a constant. All should be relatively straightforward stuff. Cool. So that's hopefully just enough context for you to understand what Djinni does and what the basic types are. And now I'm going to focus on how we implement that. You don't need to know all the details of exactly how the Djinni interface is used or declared or what the options are, so much as what it's for is calling between languages, and let's talk about how we did it. Specifically, how we did it for Python. Now, Python was a challenge for us. It turned out to be more complicated than we expected. I want to give a shout out to Yulia, our intern from Yale, who dove into this over the summer. And we like to throw in our interns at the deep end. So the reason this was a bit of a challenge was that we hadn't done very much bridging of Python before. When we did Objective-C in Java, we had a lot of prior art of handwritten marshaling that we could look at for best practices. For Python, we were kind of making it up as we went. Also, Python is a lot more distinct from C++ than Java or Objective-C. It's not a C-derived language. It doesn't have strong typing. So we had to make a few things up along the way. But these are the basic steps of the approach that we took, and I think they could be applied to any language. You have to pick what the Djinni types are going to turn into when they get into the new language. You need to figure out what your bridging technology is that lets you actually get between languages. Figure out how that bridging technology meets a few basic requirements that are kind of the basis that lets you build a bridge in the first place, and then build our Djinni-specific infrastructure on top of that. So let's start with step one, types. When picking types for Python, we want to be idiomatic. As I said, we want the classes to look natural, like Python programmers would expect. How many people have used Python, by the way? OK, almost everybody. So hopefully I'm not confusing anyone, and I'll go through these examples pretty quickly. So we want to use the native Python types that the program expects. We want to support the level of flexibility that you expect in Python, such as duck typing. And we want to support both Python 2 and Python 3, which leads to a few interesting details for us to deal with along the way. The basics, Python has numbers. We need numbers. It doesn't care as much about limited length numbers as we do, so there are fewer numeric types that we use. Python's containers map very closely to Djinni's containers. They're hash-based. If you've ever taken code from Python 2 to 3, you know that Unicode strings are one of the tricky pieces. And Djinni does its best to follow the best practices there. But it is liberal in what it'll accept. It'll take a string in any form, but when it produces its string, it'll always be a Unicode string. And bytes will always be the right representation of raw bytes rather than a Unicode string. And lastly, optionals don't have as much meaning in Python because everything is by reference and everything is nullable. But optional really just tells us whether none is considered a legal value on an argument or a return value. So let's walk through the individual types in Python. We've got records, which are just a Python class with some fields which are named. Python is pretty loose about this. All fields are held by reference, and you can add more fields later if you want to. So really the only thing that declares your fields is your init function, which Djinni generates. Sorry, I just lost my mic. Give me a minute. I'm back. All right. So that's what a record would look like when Djinni generates it. Enums, there actually is a built-in enum type in Python 3. It's available backported to Python 2, so we will generate one of those for you to give you consistent values of your enums. We use int enum, which means these enums are interchangeable with ints in Python code. It also means that when you give us an enum to make a call, you can give us an int and it'll be just as good. We don't care if you really use our enum type, but we give it to you so you can have it. So now for interfaces, interfaces are abstract base classes. Python does have abstract base classes, again in Python 3, backported to Python 2. So we will make use of that. If you choose to make use of that, then it will enforce that you remembered to add all of the necessary methods that your abstract base class requires. The way it's declared with that with meta class is a little bit weird. That's from the future module. It lets us provide code that works in both Python 2 and 3, each of which has a slightly different syntax for meta classes. But this basically works the way that you would expect. But you might cry. I said I wanted to support duck typing, and now I'm talking about specific types that I'm generating and abstract base classes that want to enforce which methods you created. So some people like strict typing, particularly if they're coming from C++. Some people don't. We want to support both of them. We give you all the classes you need. So if you want to follow the strong typing and get the guarantees that comes with it, you can do that. But as long as what you give us acts like a Djinni type, we'll use it. So like if you give us a implementation of an interface that only has one of the methods, as long as that's the only one you ever call, things will work. If you ever call one of the other methods, then you'll be pretty unhappy. Right. So that was step one. We know what we want everything to look like in Python. Let's talk step two, which is how do we bridge from Python to C++. So we use a technology called CFFI. It's out there on the internet. You can Google it. It stands for C Foreign Function Interface. Note C, not C++, which means we have to go through C on our way to Python. So it's pretty well accepted. It works in both or multiple different Python implementations, which is nice. It works on both major language versions, which is nice. It generates code. Actually, CFFI is itself a language bridging code generator, which is kind of interesting. But that generation makes it more efficient because that code can get compiled and has less runtime cost than the dynamic code you might have to use otherwise. And if you happen to have used CFFI or plan to use it in the future, know that it has multiple modes of operation, and we're using API mode out of line. If that means nothing to you, don't worry about it, because I'm going to describe how we use it, which is what that means. So here's the layers of a Python app that uses Djinni. You've got the app itself. You've got those generated Python classes that look like the examples I showed you. You've got this compiled extension module, which is what CFFI generates, which is specific to the Python implementation. You've got a C interface that Djinni generates, which is C functions that are implemented in C++. This is a common thing you've probably seen if you ever had to interact with C code before. You've got a .h file that's pure C, but then you implement it in a .cpp file. Everything's happy. That wrapper interface can then call directly into the generated C++ classes, which Djinni also generates for you, which in turn can go into your code or come from your code, where you implemented an abstract base class in C++ or did whatever you do. So these are the layers. CFFI, being a code generator itself, has some build time inclusion in your build process as well as at runtime. So you take your C++ code and the C wrappers that Djinni generated for you, build them all together into a library. Djinni generates you some code that will feed CFFI the declarations of all the functions it needs to call. It actually parses the header files, feeds them into CFFI to make sure that you have a single point of definition. CFFI, in turn, generates some C code that talks between Python and those C functions, which gets compiled into a Python extension, which is a .so file, at least on Mac, that's what it is. And the final result is that you've got a compiled binary that's optimized for interacting with Python and hopefully as efficient as possible. And all of this is done in a way that is specific to the platform on which you're running the build. So if you want to do both Python 2 and 3, you can use the same code, but you should run these build steps separately, generate two different extensions that you would load in a Python 2 or a Python 3 interpreter. So once you've done that at build time, things are pretty easy at runtime. You want to load the compiled Python extension. You can load it just like any other Python module with an import. Then this lib object lets you make calls to C functions, and it does some of the basic marshaling internally. Of course, in our Djinni-generated classes, we don't want you to call C functions. We want you to call ordinary methods. So we have a proxy that'll hide this and give you something that looks more like a normal Python interface. So let's get on to step 3, which is if we're using CFFI, does it actually meet our needs? And what are the basic needs that we have in order to build a language bridge? Those needs are, you need to make calls in one direction. You got to make calls in the other direction. You got to be able to pass data of some sort. And you got to be able to refer to an object from the other language so that you can pass it around and point to it in a call, things like that. Calling Python to C++ is pretty simple, given what I already showed you. Like we've already got that from CFFI. Calling in the other direction is not quite as simple because CFFI is only really available in Python. There's no way for C++ to talk directly to it. But there is a way to set up a callback, which can allow C++ to talk to it as long as Python sets something up in advance. The way you do that is you can decorate your function with this callback decorator. That allows it to create a function pointer that C can use, or C++ can use. And you would have to make a call into C++, give it that function pointer, and it would store it somewhere. In our case, in Djinni, it'll store that into just a global variable, and we would do all this initialization when the Python module gets loaded, so that by the time you can call into C++ and it can try and call back into Python, everything's ready, and all your callbacks should work. So how do you pass data? In theory, you can build a bridge if all you've got going back and forth are bits and bytes. That's what everything is anyway. But it sure helps if you've got some richer types that you can use on the interface. So CFFI can actually understand arbitrary C types, so we can take advantage of that. We don't use all of them. We use all the primitive types, which map directly to what we would use in C++. And then everything else is a pointer to an opaque struct, meaning what CFFI sees is a struct declaration with no definition. And all it ever tries to do is pass around a pointer to that struct. And then the struct is defined in C++, so it can hold on to standard strings and vectors and things like that. Again, this is pretty standard if you've ever bridged C++ to C. You hide everything behind an opaque structure of some sort. Now, the last thing I mentioned is how do you reference objects between the directions? Going from C++ to Python, we use one of those opaque structs that I mentioned. Stick your C++ object in there, pass a pointer to it. CFFI holds that in what it calls a C data object, which is just an object of something with a C type. In this case, a C type would be a pointer. That all is relatively straightforward. If you go the other direction, again, you've got a little bit more work to do. But it's still relatively straightforward. CFFI gives you the ability to create a handle, which is a CFFI or a C data object that is derived from a Python object. You can pass it to C++ as a void star. We actually do a cast and turn it into something with a slightly more specific type, just so we can keep it straight when we're writing our C interfaces. Then C++ can grab that pointer, hold on to it, pass it back to Python later in a callback, at which point you can call from handle, get back the original Python object. Now, I've skipped over object lifetime and ownership here. There are some tricks, which I'll get back to a little bit later. But this at least does allow you to refer to an object and reference it, find it later. So those are the basic features that you need to build a language bridge. And I think I've proven, or at least concluded, that CFFI can do that. But that is far from everything that Djinni actually wants to make use of. So let's talk about how we build some higher level concepts on top of these basic concepts. So the primary features that Djinni needs to do its work is it needs to be able to proxy an interface across languages, it needs to marshal some data, it needs to be able to own objects across languages, not just reference them, and it needs to be able to handle errors and exceptions that might come up. So we'll talk about each of these 4 things in turn. Proxy objects is just something that allows you to hold on to an object in language A that forwards all of its methods calls to an object in language B. And it needs to hold ownership so that when you're done with the object in language A, it goes away. So as you get separate proxy types, which Djinni will generate for you in each direction. So for instance, a MyModel CPP proxy is a Python object that inherits from the abstract base class MyModel in Python. It owns a reference to a C++ object, which itself inherits from the abstract base class MyModel in C++, which is a C++ class of the same name. And the proxy, when you make a method call on it, will just forward it all down through the bridge, through CFFI, through all those layers, get it down to the original object. And that's all I'm going to say about proxies for now, but stay tuned. Jacob's going to do a deep dive across all languages into some of the difficult parts of proxies that come up a little bit later. But let's move on for now to marshaling of structured data. In CFFI, marshaling a primitive type is trivial. It just does it for us. But what if you have, a record containing a list of records, each of which contains a string? All of these need individual marshaling, and you got to do all these individual steps to get things across the boundary, one at a time. And it would be really nice if each of those individual steps, it didn't involve a copy. I've already said, and we've accepted, that there's going to be one copy when you marshal an object across languages. But it would be nice if there wasn't a recursively increasing number of copies depending on how big and complex the object is. So how do we minimize that? It turns out it makes it easiest to do so if we let C++ always be the driver of the marshaling. It chooses which steps go next and drives the process. The reason that makes the most sense for us is that C++ can understand by value and move semantics, which aren't meaningful in Python, but are very important to get right in C++. And on the flip side, Python allows you to incrementally construct objects of classes and add fields as you go, whereas our C++ objects want you to give all the fields in the constructor. So this direction lets us do that, as I'll show in the next few slides. So we always generate C++ to do marshaling of a complete object. And it can call into Python to get or set individual parts as necessary. And Djinni will auto-generate the helper callbacks that it needs in order to do that. So let's talk about the first direction, Python to C++. Python will pass a reference to the whole object down to C++ as one of those handles that I mentioned earlier. C++ will then request the subparts of the object as necessary, as it needs them. That might be all of the elements of a list, or it might be each of the fields of a record. And then once it's got all those, it can construct everything at once. And all of the intermediate temporaries and copies can go away because we have move semantics or we have the return value optimization. So at worst, there might be a significant number of moves if you've got a very complicated object, but no extra copies should be done in the process. So in the other direction, we're going to take advantage of the other property, the property of Python that I mentioned. C++, when it wants to marshal an object, will ask Python to first create an empty object of the correct type. And then it'll pass in the subparts one at a time. Now, if this is a list or a dictionary, that's pretty straightforward. You're just calling add or append. If this is a record, then what we're doing is we're adding new fields to the class one at a time. But that's perfectly legal in Python as long as you've they're all there before a user ever sees it. They don't care that they were added one at a time. And everything's by reference, so there's no extra copying implied here. So when we're done, we can pass the entire object to Python, and it's complete at this point and can go in and act like the right kind of object. So marshaling objects comes with object ownership. You got to be allocating memory, you got to be freeing memory. Each language has its own different semantics for doing that. There's no direct way of owning objects between languages in Python or CFFI with C++. The way that there is, for instance, in Objective C++, where you can just mix the two languages together, or even in JNI, where there are calls to explicitly allocate and delete from both sides. So we need to do a lot of this ourselves, provide the helpers to make it happen. The basic rule that we decided to follow is that every time we pass an object across the boundary in either direction, we're passing ownership with it. So the person who gets the object, whether it was an argument passed to them or a return value passed back to them, are expected to free it later. It's always explicit ownership, and it's always transferred across the boundary. That rule is simple. It works for arguments and returns. We can check it and try and enforce it everywhere in our unit tests and elsewhere. It's possible that by doing a more complicated set of rules, you could get a little bit more performance. We might look into that later. But for now, this works pretty well for us. But like any rule, there are exceptions, which is really inside of those multi-step marshaling callbacks that I mentioned. We don't pass control of the object back and forth every time we don't try and ask for one of its fields. We let those be a special case where ownership isn't transferred. So how do we actually implement this ownership? Once it's passed across the boundary, there has to be an explicit call to delete, which goes back across the boundary in whichever direction. Wherever possible, we want to automate this with RAII. In C++, it's really RAII, and we use unique pointers with a custom deleter that will call back into Python when the object is deleted. In the other direction, there's not really RAII in Python, but we can do something similar. We have helper types that will hold on to a C object that will delete it in their del operation. And we can use with blocks that give us slightly more predictable destruction time, which just helps clean things up. It's optional because Python would eventually garbage collect it, but we think it's a good citizen sort of thing and helps us to validate in our unit tests that everything that should get freed actually did. So how do you do explicit ownership in Python? Do I have 2 copies of this slide? I do. I'm sorry. I revised this slide at the last minute, and this is the revised version. So Python is garbage collected, and it doesn't have any explicit deletes. So how do we make that actually work as a contract? Let's say you're trying to pass a Python object down to C++. You create a handle to it, as I described earlier, that creates a CData object. You pass it to C++ as a void star, but the garbage collector doesn't know anything about that void star or the fact that C++ is still using it. So it's going to happily delete both the handle and the object that it points to. So you need some way of delaying that garbage collection by keeping that handle alive so that it keeps the object alive so that nothing goes away and you don't have any dangling pointers. The way we do that is pretty simple. We put that handle into a set that's in a global variable. So then Python says, oh, that's referenced in this set. I'm not going to delete it. And then when we get that explicit delete call later, we just remove it from the set. And we can sprinkle around asserts to make sure that nobody tries to delete something that's not already in the set, which would indicate a bug somewhere. So it works pretty well. We auto-generate this set as a global variable of each class so that we aren't mixing it into one gigantic set, at least. But it doesn't really take it that much extra space or data along the way. So all the ownership I've talked about so far has been exclusive ownership. That is, objects are uniquely owned. They'll be deleted once later. That's true of almost all the objects we have to use, because most of these objects are just created and passed through the boundary once, and then you're done with it because you've either marshaled it by copy, you have a new object on the other side that is moving on and going on with its life. This is true of all the wrapper objects that we generate around C++ objects, like our wrappers around strings and binary, box types that we use for optional primitive types so that we can null them out if necessary. It also works for Python handle objects held by handle, because it happens that the way we use these, they're always uniquely, exclusively owned. So everything works. There is one case where it turns out we needed shared ownership, and that's for interfaces. Interfaces, because they can be passed around and passed to multiple calls, go back and forth over the boundary, you can't keep exclusive ownership even of the wrapper that's in the middle there, because you might pass it to another call later. You don't know which of them is going to free it. So we use reference counting. The Djinni wrapper that we generate for each interface has its own reference count, which counts the number of Python references. There are explicit calls to decref that'll come from Python instead of calls to delete that we would normally have if it was exclusive ownership. Then the wrapper holds a shared pointer, which is how it shares with references in C++, and that's much more nice and automatic, and smart pointers are good that way. You don't have to write it yourself. That shared pointer might be directly to a C++ object, in which case we're done as far as the ownership story. Or it might be to a Python proxy, which is itself holding a Python object, which it holds by a handle. But that's all OK. That handle itself is exclusive ownership. And the reference counting is handled on this, this wrapper object that might be held in Python multiple times. And so when the last reference from Python goes away, the wrapper will go away. If you pass it the same C++ object to Python again, it might get a new wrapper. But that doesn't really bother us at all. The proxy cache will make that less common. So the last topic I want to talk about in terms of kind of advanced language bridging for Python is exceptions. You might know that C doesn't have exceptions. Therefore, CFFI doesn't really know anything about them because it doesn't expect C functions to throw them. If you don't do anything of your own and an exception gets to CFFI, depending on where it gets there and from which language, you might crash. It might just ignore it and move on and return 0. That's probably not the behavior you want if you're actually running into exceptions on either side of your program. So the bridging code is responsible for catching any exception, marshaling it to the other language that made the call, and then rethrowing it as an appropriate exception in that language, so that it can keep propagating, get handled, caught, et cetera, and hopefully lead to useful diagnostics at some point. So the way we do this, we need some way of passing the exceptions since C doesn't know about them. We use a per thread state that holds on to an exception. It's basically an extra return value, a lot like what you might see with error no or get last error in your favorite C APIs. Now, I know what many of you are going to say, you hate that kind of C API. I hate them too. The reason I hate it is because it's too easy to forget to check that, because it's not in your face. Even return values are easy to forget, let alone something that's not even in the function declaration. But since we're dealing with generated code here, the generator is never going to forget to check. Well, unless it has a bug, but we'll get rid of those hopefully as soon as possible. So I'm relatively happy with using this approach because it's not subject to the errors that it normally is. So what's this per thread exception state? It holds an exception or no exception. It always contains a Python exception. We just decided to settle on that rather than the complexity of holding one or the other and translating it later, because you're always going to have to translate it across the boundary anyway. We'll just do the translation before or after and always store it when it's a Python exception. But it's actually C++ that holds on to it by handle. That's partially because thread locals in Python when interacting with C++ threads are weird. There are ways of making them less weird, but they're outside of the scope of Djinni. But inside of the scope of some sample code you can find in the Djinni repo. So we only populate this exception state while we're in the process of crossing the boundary, meaning a function call happened from language A to language B threw an exception, and we got to propagate it back to language A. Only during that time do we set the exception into this state. And then when we get back to the original language, we immediately want to check the state and clear it as we throw the exception. The code you need to do so in both directions is symmetric. It's not identical because it's different languages, but it does roughly the same thing. So if you've got a callee, their responsibility is to have a try-catch around everything they do, catch exceptions. If an exception occurs, stick that exception into the exception state, and then return. The caller, in turn, after returns, is responsible for checking the exception state. It should do that before making any assumptions about the return value, notably, such as that it's a valid object. And then if it sees an exception in the exception state, it should clear the state, and then throw that exception. And there's implicitly a translation here at some point when the exception either goes into or comes out of the state. It has to get translated into a different language. But that's just marshaling an object in a relatively straightforward way. The way we do that, Djinni provides some tools for that for you. It'll provide a simple default translation as well as a way for you to plug in your own translation if you've got your own custom exception types that you want to use to get enhanced features, like maybe back traces. The model here is almost identical to what we do in Java, and I'm going to talk about that in one of the deep dives later. So I will not go into much more detail than that right now. So wrapping up on Python before we move into the next topic, what I've described is kind of all of the basic building blocks that were relevant to us building in Python. I think they're relevant to building in any language, though that hasn't been tested yet. One nice property of the way we did this is that C wrapper layer should be reusable for bridging to other languages that know how to talk to C. We already had some experimental use of that at Dropbox with people who are trying to bridge to C#. So our Python support is mostly complete. It still has a couple gaps, but it is available on GitHub for you to try out. We just pushed it to the Python branch today, and I hope you'll check it out. So enough about Python. Let's move into some deep dives on individual features that are relevant to Python, but also to other languages. And with that, I'll hand things over to Jacob.
Great. All right. So as Andrew said earlier, we generate proxy objects when you're calling from Java to C++, or Python to C++, or C++ to Objective-C, et cetera. We get an interface in each language, and we also get an implementation of that interface that does cross-language calls. So for the example of Java calling into C++, we have a Java object with a native function, member function, which means, hey, JVM, if you go and do a dynamic symbol lookup, you should find this native C++, or C rather, function, Java under your package under blah, blah, blah. For C++ calling Java, it's something very similar. In the other direction, there's a call object method or call void method, et cetera thing. And so let's look at an example of how that's used. Let's say we have a weather report service. Well, we've got a little record for what the weather is. A weather listener is something we might be implementing in Java or Objective-C that has a function that gets called whenever there's a new weather report. And then this service will have an add listener and remove listener pair. This is a fairly common idiom that we see in our mobile code. When you call add listener, you give the weather service your listener, it hangs onto it. When you call remove listener sometime later, it removes its reference, and then you've broken the reference cycle. So let's look at the example, or the implementation in C++. So here's how we do this in C++. We just have a set of shared pointers. In add listener, we add to the set. In remove listener, we remove from the set. So my weather service is something I've handwritten in C++, and then the weather service class that it derives from is a class full of pure virtual functions, which Djinni wrote for us. And then there's some other code, of course, that iterates through all those listeners and calls them whenever necessary. OK, so here's the thing. When we make that erase call, we need to have the same listener object, even though we made two different calls through the bridge, which means our bridging, our method implementation for add listener and for remove listener can't be as simple as, OK, here's our Java object, conjure up a new C++ wrapper around it, and keep going. We have to wind up with the same thing on both sides, or else our erase call will have gotten a freshly created C++ listener and won't find anything in the map, and nothing happens. If we'd been more clever, we would have written an assert, but oops. So there are performance benefits to not creating a whole bunch of objects that aren't going to last for very long, but really this is for correctness, right? We might need identity comparisons to behave the same in C++ or on one side of the barrier as they do on the other. And this is necessary to enable idioms that developers want to use. So what we do is we keep a cache with references to all of the proxy objects that we've created. And whenever we pass something from Java to C++ or across any other language pair, we hang on to it. And we reuse it if we can. So we store a map, it's an unordered map, from a non-owning reference to the original object to a weak pointer to the proxy object. Now, I use the word cache, so I want to be careful about what guarantees I'm providing here. This is not an LRU type, evict them when we can. The wrappers don't last forever, right? If we generate a bunch of temporary objects, create wrappers, then don't need them anymore, we don't want those to hang around forever, which is why we're using weak pointers. And we only care about whether we can get into a situation where someone, let's say in C++, has two different wrappers that can pair differently but refer to the same object. We don't want that to happen. So it doesn't matter if these wrappers last longer than they should. We only care if they're visible, if someone can actually have two of them, which weak pointer gives us exactly those things we need. So here's the generic version of this cache. We used to have 4 separate implementations between each of Java, C++, Objective-C, each direction. When I started to implement this for Python, we realized, wait a minute, let's not go from 4 to 6, let's go from 4 to 1. So now this actually shares code. This is one fairly ugly template. It's parameterized over a whole bunch of different types. The cache maps from proxy objects, maps from implementation objects to the proxy objects that we already have for that implementation. And then there's this handle that the proxy object is expected to hang on to that points to the implementation. And it can use that to actually make its calls as well. And when the proxy object goes away, then the handle goes away, and that cleans up the map entries. So I'm going to go through what happens when the proxy doesn't have anything referring to it anymore. First it has only a strong pointer, or it has one or more strong pointers owning it. Then the strong pointer goes away, so the proxy object is still there. We're about to start calling its destructor. The very first thing that happens is atomically any weak pointer that's referring to that proxy object is now dangling. And this happens atomically in std shared pointer and std weak pointer. It also is guaranteed to be atomic by Java weak references and Objective-C _weak. So we have that guarantee. So now the weak pointer is dangling. OK, now we know that although this proxy object still exists, no one has a reference to it. So we start cleaning it up. First, the proxy object itself, we enter its destructor. It might contain the handle by a subobject or a member, or it has a pointer to it or something. The handle's destructor reaches back into the proxy cache and says, hey, this non-owning reference to the implementation that you have is about to go away, and the weak pointer is already cleared, so please remove those entries from the map. Then finally, the proxy object goes away. There might be other things back in the Java side that are referring to that thing that we were proxying. And that doesn't matter. Whether the implementation now goes away or not isn't our concern. And the proxy cache is a global singleton, so it sticks around forever. There's one proxy cache instantiated. I elided the types that it's actually instantiated on, but it is instantiated once per language mapping, not once per type of interface. So here's the whole thing again. That was all very abstract. So let's talk about what we do in order to wrap a Java object with a C++ proxy. So things have shifted a little bit. The proxy is a C++ object that has implementations of virtual functions. It calls into Java. So I moved it right up next to the handle because that's actually a base class. And then I put in concrete types for all of these dotted lines. It has a wrapper for a JNI reference. The unowning thing is also a JNI reference. And then there's a std weak pointer from the cache pointing into the proxy. So global ref that you see in the line from the cache to the Java implementation is an RAI wrapper. And then the raw JObject is pretty much a non-owning reference. to the JNI thing. So that's Java. Here's the general thing again, so you can see how it compares to the other direction, where things are a little more complicated. There are a few more boxes, but it's not much more complicated. So the relevant points here, the handle is something that we allocate with makeUnique, and then we release it. So it's just floating there in memory. We then take its pointer, reinterpret cast it to an integer, play the Indiana Jones theme song, and pass it to Java, which stores that as a long. The Java Proxy Objects finalize method, which could be called very late, but will probably be called eventually someday, calls back into C++ to a little helper that does delete, reinterpret cast, and then that handle goes away. The Java weakref up top is a C++ wrapper that we built around a java.lang.weak reference. And Java's garbage collector runs whenever it runs. It doesn't have the precise reference counting, precise destruction of C++, but that's OK. The only thing that matters is that the clearing out of the weak pointer, or the Java weak reference, happens all at once, sometime after there are no more handles to the proxy. So that's OK. And so it's the same layout. This used to be 2 different pieces of code. There were 2 more for Objective-C. The Objective-C to C++ and C++ to Objective-C wrappers were pretty similar, but now it's all one template. OK, so there are some gotchas. First of all, the proxy cache is a global singleton, lasts for the duration of the program, but we had it held by shared pointer from the handle. Why do we do that? Any ideas? So we used to not hold it by shared pointer, and when we were only running on Android and iOS, things worked fine. Then we started building this for OS X and Linux and desktop environments, and I got a complaint from one of the engineers. My program works fine until I try to quit it, and then it crashes. And it turns out static destruction order was causing us problems, where if we have a shared pointer that points across the language boundary in a global, and the static destructor for that runs after the static destructor for the proxy cache itself, then the world ends. So that's no good. We changed it to to shared pointer to a singleton. There's only one of these, but there's still a shared pointer holding it because we don't want it to go away until the very last file that's using this has had its static destruction run. And then the other thing is, back here, we have a strong JNI reference to a java.lang.weak reference. Well, it turns out Java has not 1, not 2, not 3, 4 different kinds of weak reference. And one of them is part of JNI. There's a JNI weak global reference. Don't ever use it. We used to use it. It turns out JNI weak global references are upgradable to strong references even after the thing that they point to has started being finalized and has sort of started going through the garbage collector process. The JNI weak reference, although not a regular weak reference, can still be upgraded even at that point, which was leading to use after free if there's a race between those 2. Yeah?
Why do you even need to delete the proxy cache?
We don't, but it's held as a... So that would be another option. We could allocate it with new in a singleton and delete that. But it's not deleted by us. It's deleted by the static destruction process that happens when a C++ program terminates normally. So destructors still run, and we want to be clean with respect to sanitizer tools and not have to write in exceptions. So those are some of the gotchas we ran into. And then finally, here are all of the different ways we instantiate this proxy cache template. It takes a whole bunch of parameters. So sometimes the C++ types are shared pointer and weak pointer. Sometimes they're wrappers around Java. We had to pass in custom parameters to unordered map because a JNI reference doesn't necessarily correspond to the identity of the Java object. JNI is designed to enable copying garbage collectors so objects can move around. You have to actually ask the JVM if you want to know whether two things are the same. And then in Objective-C provides double under strong, double under weak, double under unsafe, unretained ID types, which do automatic Objective-C reference counting for you. That's nice. We had to write our own little hasher called unretained ID hash because std hash doesn't play nicely with these funky non-standard types. But all of these are put into one traits class, and then we use explicit template instantiation. So the unordered map underlying all of this and the mutex stuff is only compiled once, and that speeds up our compilation quite a bit. It also helps with code size, since previously, before we merged these, we had a zillion different instances of what was essentially an unordered map from void star to shared pointer, or to weak pointer, which all compile to exactly the same code. But the compiler doesn't know that, and so it has to spit it out a billion times. So that's the proxy cache. Next, I'm going to talk a little bit about nullability. So a year ago, we didn't handle null at all. And by didn't handle null at all, I mean if you pass null across the boundary, you would get a proxy object that points to null, and you would be very sad. This was embarrassing. We fixed it shortly, but we changed it so that you can have a null interface, and null will get passed through to null. It was just an extra check in some of the functions. But if you wrapped an interface with optional in C++, we would dutifully add an optional wrapper around that, which didn't really have any semantic meaning. We also realized Objective-C and Java both have fairly common nullability annotations. Java has a whole bunch. And so we would spit these out for data objects. We expect them to not be null unless they're optional. Interfaces could be null. For a while, we had an intermediate state where most things were nullable, but we would insert explicit checks if you had a non-optional interface. What we do now is, for interface type, it's non-nullable unless you say it's optional. You can hook into the non-null pointer library, which I'm going to be talking about tomorrow. So we have a C++ template that represents very specifically a pointer that has already explicitly been checked for null, which is a little bit different than the GSL template from the keynote on Monday. So for more info on that, I have a talk tomorrow at 2:30. That's also open source. So that's the second interesting detail. And finally, Andrew will talk a bit about Java exception translation.
All right, I'm back. As expected, we're running a little bit short on time, so I'm going to keep this brief and probably skip the code examples, but these slides will be up, so you'll be able to take a closer look later. I want to talk a little bit about a call stack that looks like this. You made a call from Java to C++ using Java for my example, but this is applicable to Python and sort of to Objective-C, though the customizability is not quite there yet. So say your UI controller is making an update to the data model. It calls from Java to C++. The data model might call back to a listener, thus calling back from C++ to Java. You now have a call stack that has Java, then C++, then Java again. And you might encounter an error, at which point a Java exception is going to be thrown. So the JNI exception model that we're working with in Java is very similar to what I described for Python. I used to think it was terrible. I still think it's terrible. I just now know that I couldn't think of a better alternative. So each thread has a pending exception. The contract is very much like I described it for Python, except that the Java side is done for us. Java does it as part of JNI. The C++ side is not done for us, so our generated code still has to use the JNI methods to check the exception state and set the exception state. Djinni will do a default translation for you. And the way it does that is when you're returning from Java to C++, it'll check the pending Java exception. If it finds one, it actually throws a JNI exception type, which is a custom type of exception that holds the Java exception inside it, keeps it by a handle, a global ref in the JNI parlance. It'll throw that. So then the other side of this contract is before you return to Java from C++, you have to catch any exception you have. If that exception is one of those JNI exceptions, then you know it's already a Java exception, or Djinni generated code knows it's already a Java exception. So it can just stick it back into the exception state, return to Java, and the same exception just keeps propagating. Of course, if it's not a Java exception, then we need to create something else if it started from C++ as a C++ exception. So we just create a runtime exception in Java and pass along the same message as was in the standard exception. So that's free, but it's a bit simplistic. What if that's not good enough for you? If you use exceptions heavily, which we do with various different exception types, you might have custom exception types that you'd really like to see thrown in your C++ code. You might have things built into your exception types like backtraces that you'd like to be able to print for debugging information. Because that Java exception that I mentioned, even if you propagate it through, it's got a very nice backtrace for the Java parts, but not for the C++ parts. That's a big, empty space in your backtrace. So Djinni gives you the ability to customize to do things like this, which is we have some translation functions that Djinni uses when it needs to translate an exception. We define those with an attribute that tells the linker that if there's another definition of this function, use that one, don't use ours. Which means you can create one of your own, just define it, and your definition will be used as long as it's linked into your executable. So let me take an example of what you would do with this. If you have a custom my security exception that you'd like to throw, you'd like that to map back and forth to a Java security exception. Let me talk a little bit about how you might do that. So the first function you'd have to replace is called JNI throw CPP from Java exception. It's a bit of a mouthful, but hopefully the name is descriptive. It is called when there's a Java exception that has made it to C++, and we need to turn it into a C++ exception. This function's job is to take that Java exception, decide what to do with it, and then throw some C++ exception. We don't care what. I told you what the default is, but its job is to throw something. Here's what it looks like. I'm not going to go into this in depth since I don't have that much time left. But basically, we're just using the JNI interface and some of the support library that comes with Djinni, some of the helpers, to check whether the Java exception is an instance of security exception. If it is, I get the string out of it, translate it to a C++ string, throw a C++ exception. And if not, I do the default thing, which was throw this JNI exception for any other type of Java exception. And I'm going to skip that. The other direction, there's this function called JNI set pending from current, which will, its job is to be called when we know we have just caught a C++ exception of some sort. And we would like you to set the pending state in JNI with some Java exception of your choice. Interestingly, you might notice there's no argument here that tells you what the C++ exception was. The way that works is you're always called inside of a catch clause, which means you could just throw semicolon and throw the same exception again, and then use catch blocks to process it as you would. I'm not going to talk through the details. It's pretty simple. If it's the type you want, you set it into Java using a custom type. Otherwise, in this case, the default behavior is a little bit more complex than one line. So we give you a function you can call to just tell the default exception translation to run there. And it'll do the two cases that I mentioned earlier. So lastly, I mentioned stack traces. I'm not going to have time to show you code or even to talk about very much detail here. But with those two helpers, you actually can implement this. And I want to just mention the key points that make this possible. This does assume that you've got some way of generating stack traces in C++ code. It's not as easy as it is in Java, but there are libraries that'll do it for you. That'll just walk the stack and try and get symbols and do something. They're not always perfect, but they're often good enough to be very useful in debugging, particularly in a debug build. And there are two things in Java that let us do this, which is Java exceptions have a cause, so you can chain them together. This exception was caused by that exception, which was caused by an earlier exception. And also, they let you override the stack trace. So as long as you can build an array of stack trace elements, which are just some plain old data, you can stick your C++ stack trace into a Java stack trace. You can build some helpers to do it. But then the important thing is that in one direction, you put your JNI exception inside of a C++ exception that also has a backtrace. Let that propagate. And then in the other direction, you can then use some helpers to build a chain of Java exceptions where you've got a new Java exception you're about to throw, which was caused by a Java exception, which is a copy of your C++ exception, where you've copied over the backtrace into those stack trace elements. And then that, in turn, might have been caused by another Java exception. And this could, in theory, chain through an infinite number of levels. So what you see, if this gets to the top of the stack and gets printed out in Java, for instance, in a crash, so you'll see, oh, here's a Java exception with a Java stack trace caused by this other exception with a C++ stack trace in it, which might be printed a little bit weirdly because it was shoved inside of a Java stack trace, but you can use a format that is easily parsable and easily readable. And then that, in turn, could be caused by something else, and you get the normal chaining behavior that Java programmers are used to. Great. So that's all we have time for today. There's plenty of other new stuff in Djinni that we've developed over the past year. If you've been using Djinni or want to try it out, I hope that you'll go check these out. They're all on GitHub. I want to give a shout out to all of the people in the community that have contributed to this, particularly Miro, who did external types and a big refactor, who's like basically a part of the team at this point, and Stefan at Dropbox, who has made a JetBrains plugin for the JNI IDL, so you can edit those much more easily. And lastly, I hope that you will join this community, whether you want to use Djinni, whether you want to contribute to it, or you just want to share ideas. Please talk to us. Check out this talk and our previous talk online. Check out, there's a magnet link here to a Slack community where you can chat with other developers doing mobile C++ cross-platform work. Thanks, Don, for setting that up. And there's other resources like some developer tutorials that Steven's been making. And feel free to get in touch with us. Those are our email addresses. Jacob here is the primary maintainer on Djinni, so you'll see him doing most of the pull requests and processing that. But I'm happy to answer your questions as well. Thanks very much. We're technically out of time, but I will stay around to answer questions. Yeah, please talk to us. Thank you all.